Hello, and welcome to Business Calculus, Concavity, and Graphs. In the previous section, we discussed the idea of the first derivative and the effect that it had on the shape of the graph of a function. In this section, we're going to talk about something called the second derivative and discuss its effect on the shape of the graph. Pictured here, we have the graphs of the function f of x equals x squared and g of x equals the square root of x. Both of these graphs are increasing on the interval from 0 to positive infinity, but their curves have very definite different shapes. On the left, we see that the graph curves up. It opens upward. This is a property that we call concave up. On the right, we see that the graph of the square root of x opens downward, and we call that property concave down. When I look at these, the way that I like to think about them is whether or not they hold water. If we rained on the graph on the left, we see that it sort of pools towards the middle because it's bowl-shaped. If it rained on the graph on the right, we see that the water would sort of slough off like it's a roof or something. Furthermore, we can look at the relationship between concavity and the first derivative of each of these functions. The function on the left, x squared, lies above its tangent lines as pictured here. A function that lies above its tangent lines in a region is going to be concave up in that region. We see that the opposite case for the graph on the right, which is concave down. The pictured tangent lines are above the curve, and we see that that opens downward. We consider a graph to be concave up on an interval from a to b if its derivative is increasing, and concave down on an interval from a to b if its derivative is decreasing. I mentioned earlier we would talk about something called the second derivative. The property of concavity is tied to whether or not the derivative of a function is increasing or decreasing. We take the derivative of the derivative, or the second derivative, which we denote as f double prime. For a function y equals f of x, the second derivative of f, if it exists, is given by f double prime of x equals d dx of f prime of x. We have a couple of alternate forms of notation for this, which are d squared y over dx squared and y double prime, like we had the notation of dy dx and y prime for the first derivative of a function. To evaluate the second derivative of a function, all we need to do is take the derivative of the derivative. Using as an example the function f of x equals x squared, we have f equals x squared. Its derivative, because of the power rule, is f prime equals 2x, and the derivative of the function 2x, or f double prime in this case, is going to be just 2. We see that for the values of x that are greater than 0, f double prime is equal to 2, which is a positive number, which tells us that the first derivative of the function f prime is increasing, and hence the graph of the function f must be concave up, which means it's going to hold water if we were to rain on the picture of the graph. For our function g of x equals the square root of x, we have its first derivative, two derivatives looking as follows. G prime of x, again according to the power rule, is equal to 1/2 times x to the negative 1/2 power, which is equal to 1 over 2 times the square root of x. And then in order to evaluate g double prime, we take the derivative again, using the power rule. Reducing the power by 1 and multiplying by the old power out front, we see that the derivative g double prime is equal to negative 1 divided by 4 times the square root of x cubed, or 1 over 4 times x to the negative 3/2 power. Again, for positive values of x, we see that the second derivative, g double prime of x, is negative because for its functions the denominator is positive and the numerator is negative. So g prime of x is decreasing and the graph of that function is concave down, as we saw from the picture earlier. Here we have a table that shows some general notes about concavity. On an interval from a to b, if f double prime is positive, then we say that the function f is concave up. And if f double prime is negative, then we say that the function f is concave down. So a positive second derivative tells us that the first derivative is increasing and the graph is concave up. And we see some examples here of the graph opening up and some different general shapes that the graph can take. If we have the other case, where the second derivative is negative, we see that the first derivative is decreasing and the graph of f is concave down. And we see, again, some examples of what it looks like when the graph opens down. Using what we've just learned, including remembering the power rule, what I would like for you to do is to determine the intervals over which the following function is concave up. Your choices are the interval from negative infinity to 1, the interval from 1 to infinity, the interval from negative infinity to 1 union 1 to infinity, or none of these. Thank you very much for listening.